Welcome to the chemistry question. Jordan here, and today I would like to explain why sulfur and oxygen are so different. The general rule is that elements in the same column have similar chemical properties. Sulfur and oxygen are both chalcogens, so you would think that they have similar properties. However, oxygen and sulfur are actually two very different elements. Let's first look at the elements as they exist naturally. Oxygen is a colorless diatomic gas that composes 21% of the atmosphere. Sulfur, in its most common allotrope, is a yellow solid that is composed of rings of 8 sulfur atoms. Since only one type of atom is present in each molecule, both the sulfur and oxygen molecules are nonpolar. Therefore, as you may recall from an earlier video, the London dispersion force is dominant in these molecules. 2 oxygen atoms have a total mass of about 32 AMU, roughly the same as 1 sulfur atom. Therefore, a ring of 8 sulfur atoms has a mass 8 times that, or 256 AMU. Recalling that London dispersion forces are stronger on atoms or compounds with greater atomic mass, then it makes sense that sulfur would have a higher melting and boiling point than oxygen. However, sulfur still has a fairly low melting point, only about 15 degrees Celsius over the boiling point of water. The common thing with the chalcogens is they react with hydrogen to form a gas with a very strong odor. Sulfur, for example, forms hydrogen sulfide, a gas with the smell of rotten eggs. Oxygen, however, is different. When it reacts with hydrogen, it forms a common liquid, water. Water is also significantly less toxic than the other gases formed by hydrogen and a chalcogen. Of all the chalcogens, oxygen has the lowest atomic mass, so shouldn't hydrogen oxide have a lower melting and boiling point than hydrogen sulfide, as it would have the weakest London dispersion forces? This is when we have to recall another force, the Dipole-Dipole Interactions. Sulfur has an electronegativity about 0.4 higher than hydrogen, meaning that sulfur is slightly negative in hydrogen sulfide, and hydrogen is slightly positive. This means that the hydrogen atoms of one molecule will be attracted to the sulfur atoms of another molecule, a force stronger than the London dispersion, but still weak enough so that in this case hydrogen sulfide is still a gas. In water, however, another force is dominant. Oxygen's electronegativity is great enough that an even stronger force is created, hydrogen bonds. In molecules where a hydrogen atom is bonded to an oxygen atom, the electronegativity difference is great enough to where the positively charged hydrogen is quite strongly attracted to the negatively charged oxygen of another molecule. This allows water to be liquid, while hydrogen sulfide is a gas. Another allotrope of oxygen is ozone. Ozone is not as stable as diatomic oxygen and has an unusual feature. It is often seen drawn where the central atom has one free electron pair and has a single bond to one of the terminal oxygens and a double bond to the other. In reality, the double bond does not stay on one pair, and in fact quickly alternates between the two pairs, so that each can be said to have 1.5 bonds. In other words, the bond is delocalized. The exact same holds true if the central oxygen is replaced by a sulfur atom. However, when sulfur is the central atom, sulfur trioxide can also be formed, which is interesting because oxygen can typically only bond to 2 of other elements, yet sulfur does not necessarily follow this rule. While oxygen only has electrons in the first 2 energy shells, sulfur also has electrons in the 3rd energy shell. Only 2 electrons for both are needed to reach a noble gas configuration, which is why they both often make 2 bonds. Being in the 3rd energy shell gives sulfur an advantage, however, it has space for extra electrons in the unused d suborbital, which is later used for transition metals. When sulfur forms bonds, it can put electrons in the d subshell and form what is known as an extended octet. Sulfur can make up to 6 bonds, as can be seen with compounds such as sulfur trioxide and sulfur hexafluoride. This means its valence shell can have 4 electrons beyond the standard octet. This extra freedom means that sulfur can much more often be the central atom in a compound than oxygen. Thank you for watching the chemistry question. I hope you found this interesting. Be sure to subscribe and leave any questions or suggestions in the comments below. Until next time.